Request, Radha, I just mute on now. Okay, I'll mute on and then I will ask you to unmute yourself. Otherwise, everybody will be talking. Okay, you try to unmute your
mute on and then I will ask you to.
Ma'am, in YouTube it is streaming, ma'am, no problem.
Okay. Radha, can you just unmute?
Yeah, sure.
Okay, fine. So we'll start now. But okay. And all others, I request you to stop the video also because the bandwidth problem will be there. More participants are there, so kindly cooperate. So good evening to all the participants and the guest speaker of today, Dr. Radha, Professor, Department of Chemical Engineering, AC Tech, Anna University. And today we are going to have a wonderful session on concept of green engineering and its environmental impact. We are on the second day of our faculty development program. I welcome all the participants and the speaker and every one of you to make the best use of the session. So let me give a brief introduction about the speaker. We have Dr. K.V. Radha. She's a professor in the Department of Chemical Engineering, AC Tech, Anna University. And she did her bachelor's in chemical engineering in Annamalai University and her master's and PhD from Anna University. And Radha is passionate about developing sustainable green technology, and her current interests cover up design of a material, product, process, and system. And prior to joining to Anna University, she had worked with Central Leather Research Institution and Pounds India Limited as researcher in their research division. And she has more than 80 national, international research papers and conferences. And also she holds a patent on green material for adsorption process. And she leads the bioproducts group in her department with UG, PG, and PhD scholars working in green technology. And her special interest include research on nanomaterials for energy, air, water, and soil pollution treatments. And I'm very happy to introduce that I am also a classmate of Radha. I was there in chemical engineering department for a few months. And from then on, we are very good friends. And she's a very dynamic lion woman amongst our female gang. And very, very happy to invite Dr. Radha to take over this session. Dr. Radha, over to you.
Thank you, Dr. Ushaa. Your introduction really has kept me high in this evening. And I would like to say that this is my first online conferencing apart from my own class. Now I can see so many other people, mixed gamut of people entering into the system so that we'll be able to communicate with many people around. And utmost first thing I would like to thank Dr. Ushaa Eswaran, CEO of C, who is bridging the gap between the parents, students, academics, and the industry. A high motivator. Once we listen to you, anyone in life gets motivated. I really congratulate you on that aspect, Ushaa. And I really thank Anna University for giving us research facilities, research freedom to get into the field. So whatever the research, university sees to that they excel in it, and they give us all sorts of facilities. So I thank Anna University, and because of it only I'm here before you, Ushaa. And can we go into the presentation?
You can share your screen and kindly disable the annotations before you start.
I think I have done with it.
I don't know. You have to check the settings whether your annotations are disabled. Settings of Zoom. You'll have a more option there, no? In settings of Zoom.
Like, I think there's a cross over there, the annotations. I think I have done it.
Okay, then you can start presenting.
I can start with my presentation. Am I audible to everyone?
You have to go to the play mode.
Can I start with it now?
Yes, start.
Good evening to everyone present over here. After the introduction, also some people have entered, I feel. Dr. Ushaa gave a very warm introduction about me. And those who have just now entered into it, I would like to say that I'm Dr. Radha, working as professor in the Department of Chemical Engineering at Nine University. Today, my topic is going to be on concepts of green engineering and its environmental impact. Talking about green engineering, and I would like to say now itself, so many people are there. So much of green will be the word I'll be using now. So you need to be really patient with me because this is all about green engineering. So what is green engineering? We can say that it is the term of the safety measures. So whenever we think about the term in any mahals, we need to look into it. So we need to look into the green aspects. So it has a hierarchical approach of bottom up rather than top down. In industries, we always start with workers' safety because it is a bottom up approach. Workers' safety is more important, and then comes the employees' adaptation to newer measures, newer methodologies, manufacturing devices, engineering controls, and which need to eliminate the substitution reactions. Unless we are going to eliminate the substitution reactions, we cannot enter into green technology or green engineering at all. So the elimination of exposure, even before it occurs, has to be eliminated. So we need to think about the practice which started in United States. That is with the passage of Pollution Prevention Control Act in 1990. So we can now think this is a newborn baby of green concepts. Just 2 decades ago, everything started with. So now looking into the Pollution Prevention Act, which they started it, what they actually entered into is, that is, they established the policy to prevent and reduce pollution at its source, wherever feasible. So here we are using the word wherever feasible is, everything cannot be eliminated or dismantled, only wherever feasible we can go for it. And now this reducing pollution at source can give the act named as fundamentally different and more desirable. So when we are using chemicals, naturally you get a good products, but we need to change the concept at all. So we need to go for fundamentally different process. So this EPA green chemistry, the program which US started, build the collaborations not only with academia or with industries, but it also started with all the stakeholders, be it government organization, be it non-government organizations, or any pollution prevention organizations through green engineering. So why do you want to go green? What will happen if I'm not going to go? Sure, it is going to be extinction. No further development. We need to have a dark society now. So we need to enter into this green society or green engineering so that we get a beautiful atmosphere where people can breathe easily. So the invention of steam engines itself started with the industrial revolutions. Our planet had suffered rapid changes in climate.
Excuse me, Radha.
Yes, no? Yes, Usha.
Have you started presenting the slides? The slides are not changing.
No, I have not changed it.
Okay, okay. And
I
go to
just,
play mode, Radha, please.
yes, ma'am.
You have to go to the play mode. You have not gone to the slide play mode.
Yeah, 1 second. Actually,
That you have to click, yes.
yeah, I think it's going on.
Not it.
One second. Just a second. One second, Usha.
Yes, yes. Yeah, yeah, I think now it's fine.
Now it's right.
Yes, yes.
Video.
Now you have to share. Yes. Yes.
Yes, right.
Yeah, let the slides come
Is it
in.
okay now?
Yeah, fine, but it is not playing again. Yeah, it's fine.
It's playing now.
Oh, it's fine. Yes, yes.
Okay. Shall I continue now?
Yes, yes, please.
So whenever we are going to talk about green, then we say will be extinct forever. Now, talking about the intervening between the green concept and present day how it is. So we need to see down the process are irreversible. The green concepts once we introduce, the process should be irreversible. We cannot go back again and again to change and clean the system. So we need to think about some processes where we can actually think of entire elimination and reduction of waste. The world now has only fixed the amount of natural resources. So we need to think about saving these natural resources, and some of which we know that already are depleted or it has been ruined. Say, for example, when we think about batteries in household items, these batteries have got large amount of chemicals which is present as such, and we are just putting out into the atmosphere. What happens now? These dangerous chemicals enter into the liquid stream, that is a water stream, enter into the soil stream, and these enter in as fertilizers into our own agriculture crops, and that is where we start depleting the system as a whole. And a very famous example, we can think about the plastics. Everyone we know that, but still we are not unable to stop plastics because we have come down a lot from manufacturing process. We cannot go back. But how to stabilize this? At least later on, we won't be able to degrade more. For this, we need to think about the water. Say, for example, suppose we are going to drink water. Having water, very good for health, very good. Everything we have a better environment, better health, everything. But drink water with reusable plastics, reusable utensils. So in Indian culture, we had the better environmental procedures which we all can be proud about. But we have started taking up Western culture. So we are not able to see how we are depleting the nature. So we know that it's very tough now. Okay, let me have some positive thinking about all that, thinking about green also. One thing is a very good business now it is. Everyone we know. Once we enter into the malls we see, immediately we pick up something organic. Forget about whatever the prices, we take them organic. So it is a very good business now. So people can enter into green manufacturing process. And consumers, they don't know, actually they should know. Actually, without knowing itself, some people are buying. They should know actually what is the cost behind it and how this energy is reduced in this. So once they really know the concept, then consumers will never enter into hazardous chemicals later on. And even making small changes can have a large term impact. Say, for instance, the waste created by the plastic water bottles that we can see for as an instance. Now, what is green engineering? That is the thing we're talking about for the introduction. So this is a statement. Always we have a clean statements for any technology. It is the design, commercialization, use of processes and products in a way that reduces pollution, promotes sustainability, minimizes risk to human health and environment without sacrificing economic viability and efficiency. These words, without sacrificing economic viability and efficiency, is a major loophole for many people for not entering into green technology. So as we can see there, the chemical processing. So now it is impossible to imagine modern life without chemical processes. What is these chemical processes about? It is all about, right, starting from our early morning toothpaste, toothbrush, till our late night dinner, where we take everything only through the chemical manufacturing process and other things. So what we need to do now, all its credentials we all know, but it has come to a standstill because of the severe pollution it is creating on our environment. People are talking about GHG, that is the greenhouse gas emissions, carbon dioxide, methane, nitrogen oxide, NOx, everything. So whenever people talk about, it is about carbon dioxide pollution, but more than carbon dioxide, it is other gases that is entering into the atmosphere that really makes us, causes the ill health to the public. So while human destructions of ecosystem has occurred for centuries, impacts are now accelerating and are increasing globally in nature. The term ecocide is now familiar with. What is this ecocide about? This ecocide is a deliberately, systematically destruction of the ecosystem. Deliberately and systematically you are destroying the ecosystem, that's the ecocide. So we need to eliminate this ecocide. One common major example is Amazon destruction. It is, we don't know, still it is in debate. It is man-made or natural disaster, firing in Amazon forest. So ecocide is a major terminology now has come into existence. So we need to somewhere stop this ecocide. And whenever we are thinking about natural disasters or chemical pollution companies, we think about chemical engineers. And chemical engineers are usually termed as universal engineers. Why we say it? Because they, in the Tamil we can say, Al Padi, Adai Padi, the same way it is, scientists and engineers. They know more of science rather than any of the chemical, any of the engineers. So always chemicals are pulled into for employing them into the workforce where they can find solution for sustainable development of human society. So green engineering has become the frontier modern chemical engineering, and it is a key significance to address global challenges in resources, energy, and environment. The other potential greenhouse gases which I was mentioning here are, everyone will be aware of this, CFCs, depleting the ozone layer, the nitrogen oxides, and the other volatile organic compounds. And these are much more hazardous in nature than that of the carbon dioxide itself. So now we need to think about the processes actually which is entering into the system. The objective of green engineering. What would be the objective? So before the left hand side, you can see the yield and feedstock. So whatever feedstock you're giving, this is the yield. I'll get into the process and I'll have a good lump sum amount when I enter in, when I get my product and sell it. And now it is not so. It is the yield. The combination part is the feedstock, regulatory compliance, and other ethical issues that it has come into picture. What is this yield all about? The yield is the ratio of the amount of the product that is sold to the amount of the product that should have been produced for sale. So the yield is the one all chemical engineers, all industrial person, manufacturing person is concerned about. But as a green engineer, we are now concerned about the feedstocks. These feedstocks should have no emission policy. All the feedstocks which we are having should enter into the manufacturing and come out as a yield. So the companies have to continuously improve health and safety in order to go for a clean process and thereby preventing the pollution. The establishing the process for potential industrial chemicals and consumer products should be considered sustainably green, and coordinating new joint research efforts. So this is where we all enter into the picture. So each and every day we need to have research that has to come into a picture so that new and newer products will be entering into the system whereby we have a clean technology. Because the green technology is all about green engineering, green technology, environmental technology, materials technology, whatever say the word green enters into the picture. It has to be a clean technology where we don't have any pollution in any form. So the scientists earlier have discovered with few principles of green engineering. Actually, this has been created by chemists because whatever it is, the chemistry are the backbone of any invention and manufacturing. They start at the lab level and we enter into the industrial level. And this principle of green engineering is an holistic approach. They have to integrate it into EIA, that is Environment Impact Assessments. And we need to conserve and improve natural ecosystems while protecting the human health and think about this life cycle thinking, that is life cycle assessment, that is from cradle to graveyard. So we need to think all about this whole system, life cycle assessments, so which are going to be safe, benign, and we are using only the natural resources. And we need to strive hard to prevent waste. Additionally, in order to think about the first few principles, we need to have a cognizance between the applied engineering along with the geography, aspirations, and cultures. We cannot let each and everything. And this creates an engineering solutions where we can improve, innovate, and then talk about sustainability. This actively engages communities and stakeholders in the development of engineering solutions. So companies, I could give an example for this. A company, DuPont, which every one of us knows, they have adopted totally zero discharge, zero waste. And what they are using is whatever it is going to come out of the process, they are reusing and recycling, the famous 3 R's, which we know already. And their drive towards zero emission gives priority to those emissions and pose the greatest potential risk in health and environment. The zero discharge approach has led to the development of new processes for them to think about an environmental sustainability. They have taken into consideration. So this is the 12 famous principles of green chemistry. So we'll see one by one. But who has coined these 12 principles? Because these are the 12 principles which each and every industry has to now adopt to, or else they are not at all green engineering industry. They cannot pose themselves as green industry. Because nowadays, Environmental Pollution Agency and acts are becoming really very harsh on industries. This was in 1998. They started this set of principles by famous chemists. Two people, one is Paul Anastate and C. Warner. They have started with these 12 principles, and they have said that they have to reduce the environmental and health impacts of chemical production, which indicate the research priorities for the development. And what is this research priorities about? In United States, the EPA, the Environmental Protection Agency, played a significant role in green chemistry through the green pollution prevention programs. When at the same time when US started with this, UK also entered into picture because they never go behind. They started with establishing green chemistry network, and they, with the help of the Royal Society of Chemistry, RSC, once joining hand in gloves, they started many of journals, especially for green engineering, so that more and more of research is entering into, and these research, once they come into the outer world, the industries can adopt that mechanism for their own benefit. And lots of agencies, namely, which I can say is Green Building Council, that is for green building, and then for renewable energy, for alternative energy. And these are some of the agencies with the US and UK, where they have started with many more applications towards green chemistry and engineering. So let us see one by one step, because I'll take little time over here, because this is a basic principle which we cannot leave out in any of the green engineering. So unless we know about what actually it is, we cannot even say we are green engineers or green chemists or clean technologists or environmental engineers. The first one is on prevention of waste. Here I can give you little time to look into the lot of waste, and people can just see the waste, and then they can think over which are the waste which are coming out of each industry. Of course, we can broadly classify as liquid, solid, and air pollution. But really the explosion is too much. And now we are going to see that this polluted figure is going to increase enormously, and we cannot do that for the next generation. Here I would say that one of my students, when he was somewhere around first or second year, he was saying, "Ma'am, your generation is the best generation." I asked him why. Then he said, "Ma'am, you are people born in your generation, they have seen a greener world, they are seeing the other side part of the world also. You have taken everything naturally, and you have seen both sides of your world. But we start with only the filthy world." Then it really took a second for me how to say words to him. So not only for me, this is the case for each and everyone. We need to think about this. The waste, and especially solid waste, it's very, very tough. Not only that, if you can see in the slides, the automobile waste, the biomedical waste, where that lady is standing there, biomedical waste is into that. So how to go with it? How we are going to solve this? How we are going to prevent waste? Unless and then we have a methodology in the manufacturing process itself, we cannot do it. So it is better to prevent waste than to treat or clean up waste. That is, after it has been created. So we need to think the waste is better for position. Rather, prevent the waste is a better option. Normally, a very big company says that the user is paying for the waste. You can ask me how. The first payment, when the material is entering into the manufacturing process, we pay for it. The second payment, when actually the material is being separated and our product has to come to us. And the third payment, whatever is coming out as a byproduct, that we are going to pay, because he needs to let it out. And the fourth payment, a fee that is added for the collection service. So how much we are paying extra for this waste. So that really is a matter of concern. For this, we need to think about the process mass intensity. It's a chemical engineering word, which expresses the ratio of the weights of all the materials. Let it be water, solvents, raw materials, reagents, any processing aids. The ratio between this weights, that is a material, to that of the active product formation. This is where the process mass intensity is all about. This is an important focus because historically a large amount of waste are co-produced along with the manufacturing process. So suppose we are going to say 100 kilos is being produced. Per kilo is their waste. So you can imagine 1 is to 100. In terms of tons and kilotons, then we can imagine how much of waste is being created then and there. So we need to have a prevention of waste. The second one, it is about the atom economy. What is this atom economy? Actually, whatever enters in has to go out. The famous saying Mahabharata also says that. The famous principle in chemical engineering also says that the process calculation, mass in should be equal to mass out. Energy in should be equal to energy out. So what is this? If you see the triangle over there, we have the stoichiometric reagents, just exactly half. So that is a 50%. So whatever the mass in has to come out. We give this stoichiometric equation. So we need to clarify it. That is, nothing is accumulated anyway. Nothing is coming out as a byproduct. If at all it is going to come as a byproduct, it has to be utilized somewhere. So this is the atom economy. So the 100% means we are using rearrangement reactions so that nothing is wasted. 0% means no reaction at all. Nothing, a reaction is not at all going. So somewhere in between the stoichiometric reactions and the non-reactions is the chiral reactions, the substitution reactions, elimination. All these are the major culprits which is entering into the system as a waste. And if you're going to go for the catalyst reactions or addition of rearrangement reactions, then we can come down with our waste production. So the percentage atom economy is calculated whatever the mass of the desired product, that divided by total mass of the reaction into 100 will give you my percentage atom economy. So well, let me say it with this simple atom economy, whatever I have shown over here, that is isobutanol along with sodium bromide and sulfuric acid giving 1-bromo-2-methyl propanol. So this along with sodium bisulfate and water is being produced. So actually when you see here, the total is around 275 atoms that is entering into the as reagents. What is actually utilized is 137 and what actually is coming out is 138. Then exactly it is 50% that is being wasted. Now we need to think about a catalyst so that introduced into this reaction so that it gives a perfect 100% economy. Of course, 100% is an ideal, but always we can think about fewer, like to say around 90%, but not below 90%, so that we can have a economy in atomic using the atoms. The third principle talks about less hazardous chemical synthesis. I will say about this, that is what actually people are saying is wherever possible or wherever practicable, methods should be designed to use and generate substances that possess little or no toxicity to human health. So they use this word wherever practicable. So it has two principles, two parts, where we can think about whether it is practical or whether it is impracticable. Impracticable, okay. But when it is practicable, we need to start using less hazardous chemicals. So on seeing these two, for the first one on the left side, you will see the polycarbonate synthesis using phosphate. So here we can see that it is highly toxic, where it is being utilized by the chemical substitution reactions, and we use no catalyst for this, and we come out with polycarbonate synthesis. But when we are going with the bisphenol that is seen below that, bisphenol with diphenyl carbonate, with the same polycarbonate is being produced, where we can, it is a solvent-free synthesis, it is a less hazardous chemical synthesis. And talking about acrylamide to polyacrylamide. This process is highly toxic, and this acrylamide is being documented as neurotoxin. So think about the people working in this chemical industries. So people started with the new reagent, vinyl formamide, which is an isomer of acrylamide, but this is not going to be toxic. And this reagent, that is vinyl formamide, unfortunately exhibits a cost disadvantages. So if you ask the manufacturer, he'll go for acrylamide. That is a simple polymeric processes. But when you're going to talk about with green engineers or green technologies, even the cost, but here you are risking the health of the workers. That is surely condemnable. So we cannot risk the role of workers. We need to take care of them rather. So the next is on the safer chemicals. What is the safer chemical? Okay, we're talking about less hazardous chemicals, and what is the safer chemicals then? All chemicals are safer, everyone would say. All chemicals cannot be safer, or neither safer, or how to make chemicals safe. This is where environmental engineers actually come in. The chemical and materials used in effective chemical transformation matters for chemical engineers and chemists, and they need to pay more attention to the choices they make about on the focus of energy on the synthetic pathways. Occasionally, chemists do produce molecules that have toxic or other hazardous effects. And the next principle on effective, safer chemicals will always be chemical products that has to be designed to preserve efficacy or function while reducing toxicity. Here, toxicologists come into existence. What all these toxicologists say? They prefer chemicals, and then they give a green safer systems, and the chemicals are marked with the safety chemicals list. Here they say green circle represents safer chemicals, green half circle less safer, yellow you need to be careful with, gray please never use it. So all this with unnecessary derivation like blocking groups or protecting groups has to be avoided. We need to go for minimizing the toxicity. And now it is the ideal time to develop a comprehensive and cooperative effort between the technologists and the engineers, focusing on the training of the next generation of scientists to design safer chemicals. Or we need to deal everything with respect to the toxicologists, and once they say it is going to be gray, then we cannot go back to green chemicals. So let us now think about only the first 3 types of chemicals that has to be used. So let us minimize the toxicity. Let us not generate waste. That is the 4th principle of the green engineering. Now coming to safer. Okay. Solvents, we know what is the best solvent, and all other solvents will play a key role wherever they exist. Without solvents, no chemical processes. And we can always say 100% chemical processes are not there without solvents. The use of these substances, the auxiliary substances such as substrates, separation agents, everything is a solvent. Wherever it is, we need to have a solvent. Unless without solvents, the separation agents cannot occur at all. They are active in mass and energy transfer, and without this, many reactions will not proceed at all. It has also been shown that the solvents account for 50 to 80% of the mass in a standard batch chemical operations. Depending on whether water is added, water is not added, 75% are solvents. And even they say, even if it is water is going to be the best solvent, we cannot use it at all. So the solvents are always the major contributions to the overall toxicity profile. And because of that, compose the majority of the materials of concern associated with the process. On an average, they contribute the greatest concern for process safety, and they are major flammable substances also. So we need to be really careful when we are going to go for solvents. And for this, catalysts play a major role when we are going to think about this exploration and development of new synthetic routes. And these will be strong supported by the catalyst, and especially when it is going to be biocatalyst. The next principle is on energy efficiency. Energy efficiency, when it comes into picture, all chemical engineers will think about Gibbs-free energy, talk about energy in terms of heats of formation, heats of reaction, heat of combustion, everything. But when it comes to chemists, who are the basic producers of any manufacturing process, they never think a damn about energy, because energy intensive processes are frowned upon in green chemistry. We need to think about how to save energy, how to utilize energy, how to non-stop this energy which is not being conserved. We need to have these energy requirements that should be recognized by the environmental and economic impacts. You know, energy is the one leading us in all forms of life. Either it is going to be automobile, either it is going to be a solar, whatever it is, the energy is the major forms, and they are and our engineering is devoted to heating, cooling, separation, and whatnot, like thermodynamics, electrochemistry, pumping, and everything. Collectively, we can say we are more concerned on energy activities. The majority of the energy that is produced is based and will continue to be based on fossil fuels so far. But now we are entering into a system where we need to think about other energy sources. The other energy sources here we can see, it can be solar, wind, geothermal, hydroelectric, biomass, ocean energy, hydroenergy. When all other countries have entered into alternate energy sources because depletion of fossil fuels already are aware of, India is still starting brimming just now. And we can see that the India's energy basket, where only it is fossil fuels. And we can see the alternative energy is very, very minimal. So now we need to expand and close this blue circle rather than that of the, and enter this green shade more. That is the alternate energy sources we need to think about. And thinking about other sources, and more in part of the reaction or process during the design of new molecule in terms of chemistry I'm talking about. And it is critical not only on the standpoint of energy, but also from different angles. Say, like thinking about how to arrange a synthesis, or how to have the fewest number of steps, or use the lowest cost starting materials, or any other aspect of interest. We should think about just another design parameter rather than having an older parameter and then rethinking about these parameters on a major schedule which we need to concentrate on. So when we talk about the next principle, it is the renewable feedstock. That is principle number 7, renewable feedstock. This is nothing but the continuation of the previous one, where we are talking about fossil fuels, which is depleting, and presently it is around 86%, and which is going to be 96% in terms of organic chemicals. And by 2025, energy demands are going to increase by 50%. What you're going to do with the energy? We have a depleting energy, we have a fostering energy. Fostering energy, we can always concern about. And this I've shown in the pictorial diagram how bio-based energy will entering into the renewable feedstocks. The nature produce around more than 150 tons, I believe exactly, or somewhere around, and we use only around 3 to 4%. But actually, what is it is we can use more amount because it is renewable. Why we need to talk in terms of depleting feedstocks? We'll go for the renewable feedstocks. And as our famous saying was, whatever above the earth is consumable, whatever below the earth is not consumable. Let us not think about what is below the earth and let us think what is above the earth, so that renewability is a possibility. And here when we talk about this carbon footprint, what is this? We can easily think about the C in and the C out from form of energy that is used as a carbon footprint. Suppose C in is far greater than C out, then naturally it is a way of reduction of global warming cases. So we need to have a large amount of C in rather than a large amount of C out. So we need to think about this carbon footprint, which is again a major point which we need to deal with. And so many researchers are going with respect to the carbon sequestration, carbon footprints, analysis, etc. So now coming to the next principle, that is reduce derivatives. And this is more of a chemical term where we need to think about derivative reduction. That is the protecting groups which are often used in chemical synthesis. They alter the entire process. Without this, chemical process will not lead upon to a better product. But now we need to think about something which we can always use, and then we can have a better product with lesser environmental pollution. And here is a bio catalyst, that is an enzyme, which are highly specific in nature. They can be used to target particular parts of a molecule structure without the use of protecting groups or other derivatives. And it is going to act as a catalyst. It is a biocatalyst. That is from the protein structure. So we can always go for this biocatalyst rather than a chemical catalyst or a solvent which will relatively reduce the derivative. In the US Department of, here I would like to say, the US Department of Energy, they came out with the vision of bioenergy and waste products, where they established this biocatalyst for many of their production system, that is their manufacturing system. And they have said that by 2030, a well-established manufacturing process, chemical processes will be with biosystems. So they are looking ahead in terms of their chemical processes with biocatalyst, without solvent. Even if you're going to use solvent, it's going to be only water. And here they have entered into the biotechnological process where they are looking into less derivatives and less pollutions. And I would like to say over here, this derivatives when my PG project, which I was dealing with, is penicillin acylase. It is a enzyme obtained from organisms, and this is being used at large. This I was working with SPIC when they have been doing it during my PG days. This penicillin acylase made a dramatic change in penicillin production. Before it was chemical substances which were used as a catalyst, and later on it shifted to industrial process where the synthesis has been largely replaced by newer enzymatic processes. And this synthesis occurs in water at just about room temperature. So here you are utilizing the energy and the process is much more safer. Now coming into catalyst process. These catalysts I was talking about is again about the biocatalyst, which plays a major role in any chemical processes nowadays. And they have catalysts are just initiating the process much speeder. They never enter into the process. And green catalysts have a special characteristics such as high activity, selectivity, and stability, and they can be easily separable and reusable. And reusable factor is a major process, because it is always that prevention is better than cure. And we need to explore a large new synthetic routes and chemical process that rely strongly on process and catalysis. The design and use of green catalysts and catalyst systems to achieve the dual goals of environmental protection and economic benefits is an important task, and it's essential for the sustainability of the, because catalyst itself is a major area. It will naturally take more. At least it can be, we can have it as a full semester course itself. So we cannot explain much on now, but catalyst has to be discovered, and it is being discovered each and every day in today's research. The next principle is on design for degradation. What is the design of degradation? And we can see how much time limits for each and every degradation. So even before the start of the process, we need to think about the end system. That is, whether the product is going to be degradable, whether the byproduct is going to be degradable, whether all the manufacturing inputs and outputs, everything is degradable. So we need to think about this. So green chemistry practitioners aspire to optimize the commercial function of a chemical while minimizing its hazardous. Here I would say the principles of 3, 4, 5 and 3, 4, 5, they designed to reduce the hazards of the chemicals. But this principle, design on degradation, it falls into the order of reducing risk or the probability of harm occurring. So we need to think a lot. This is the basic and best part of entire principles, I would say. So the exposure to persistent chemicals can play a significant role. And we need to have regulations in order to sustain these regulations. So we know politics play a major role whenever we are going to go for degradation, and we need to think about the future. If biodegradation, hydrolysis and photolysis can be designed into chemical products, it will take us to a much greener society, and we can have a better environment and universe for the next generation where they can actually enter into it. So the real-time analysis. What is this real-time analysis about? It is the analytical methodologies. So whenever we are going to talk about something production in lab, we need to think about in online system also. And here the speakers yesterday and the speakers who are going to talk about, they'll be talking about all this real-time analysis, but we chemical engineers are not much aware about. But our process engineers do a better role here. It is monitoring and control prior to the formation of the hazardous substances. So here, how to go about monitoring? It can be inline monitoring, it can be online monitoring, or it can be both. While the traditional roles of analytical chemistry, also advanced green chemistry goals, the application, that is the effective application of process analytical chemistry, directly contributes to the safe and efficient operation of chemical plants. This is a worldwide analogy. So we need to think about the system even before entering into the actual production stage. So this will save us a lot of time and lot of spoilages of the economy, as well as with respect to the individual manufacturer profit. The last, the accident prevention. So OSHA is created its own principles on health and science channels. Again, this is a bottom-up approach where we need to think about the workers first. So we need to think the safeguarding of the workers. So let us think about a worker working in a hazardous chemical environment. Naturally, how we are going to prevent it. So we need to think about this. First thing is coming out with this hazardous chemical at all. Even in certain cases, the toxicity level in the, suppose the nuclear reactor, definitely it is highly toxic and he has to work, but how to come out with the safety precautions. So we need to think about the substances that are used in chemical processes should be chosen in such a way that it has to minimize the potential for chemical accidents, including releases of explosions and fires. And talking about chemical industries, immediately coming to even a few weeks back during this last month, we nowadays hear so much of runaway reactions, the polymerization reactions. We come across so many hazards, chemical plumes, incineratives, noise, landfills, regulated measures taken to avoid. In spite of it, if suppose we can now see that if suppose we are going to close the plant for a while, then the pressure develops, the temperature develops, there is a breakage in the chemical reaction. So it is going to be a runaway reaction, then hazard takes place. So we need to take take a lot of consideration for the accident prevention, because we are dealing with man, human, where we need to concentrate much of that. So these are the 12 basic principles on which green chemistry is all about. And from here, taking all these principles and other things, we will need to think what is the role of engineering here. This actually, we need to think about the environmental remediation in terms of an engineer. What are the things we need to think about in terms of air, in terms of water, in terms of soil, and what can be done to develop design implementation. So we are producing something in the laboratory that has to be researched. Then it has to enter into the industrial process. Then we think about the industrial environmental remediation processes. So this will give a clear picture how a conceptual design from a layman point of view or from a student level that is entering into the implementation. Initially, it will be the conceptual design which just gives a spark in the younger minds. Then experiments are being carried out. And these has to enter into the material balances and energy balances that has been with respect to the properties which are actually controlling the processes. Then the validation enters into the pilot plant level, and then the process simulation processes, and finally the process product that is going to come out after the implementation. In all this process, it is a vast process where we need to think each and everything. For example, I'll say a simple chemical reactor, somewhere it is coming into the in-between properties. A chemical design itself is a chemical reactor itself is a big complex process. You have to need the define of the objectives, say reactor operation, production rate, purity, minimum pollutant generation, selection of chemistry, that is the processes, the reactor part, the catalyst, the solvent, the concentration, the type of reaction, everything. The selection of condition of the feed, that is the material input. It's a reactant proportion, concentration, temperature, pH, and pressures and everything. The selection of reactant type, what will be the type of reactor, what are the precautionary measures we need to take in case of energy over a certain period of time, if it is going to be running with high energy or it is going to stop energy. Suppose a polymerization reaction means in between the polymer, there is a variation in change in concentration, how we are going to come up with everything plays. So it is not a simple process, but it's an extensive research that has to be done, because the methodology which we are going to give in as a green engineering has to be adopted by everyone. So even before entering into the system, we need to think about the input, the process, the output, and how it is going to change the system. So suppose we say the input, the material and energy. The input is whatever the mass in and the mass out. So suppose you are going to say about the material, energy and other things. It will go enter into the process. The materials and other, the chemicals, energy, water, everything we can put. The process is the manufacturing system. It can be extraction, it can be there is upstream and downstream process, everything we put into one stream process. And then the output, which is going to come out as byproducts, energy, waste in all forms. So whenever we are going to think about this process, we need to think about the atmosphere, hydrosphere, biosphere, and lithosphere. So far we know whatever is there in the atmosphere, there is your global warming, your ozone depletion, and your smog formation, acidification, causing human health through air pollution, and then the hydrosphere, whatever they're letting into the river was stream, and it causes again acidification, river eutrophication, and other all concerns with respect to the water resources, and then with respect to the biosphere. What is going to happen in the biosphere? It is a soil depletion, deforestation, a resource depletion, and so on. And what about the lithosphere? Still, we need to explore. We don't know what is happening. And we need to think a lot on this aspects. So, as a greener engineering, we can think about a lot of processes, and we need to have a wide variety of experimentation procedures, then enter into the system. The conceptual design itself should have a better understanding of the system. So far we have seen about many of the processes and other things. Now let us look into some greener productions. Of course, people have entered into productions and they have entered into commercialization, and in US and UK already people have started using the greener production processes products. And here I would like to say a few examples even before entering into these some live examples. The General Mills, which is being operated in US, they have come out with the landfill processes. So then when they started with this landfill processes, they thought about using this byproduct, which is coming out as oat hulls, oats, that is the hulls of the oats. They started incinerating it. Once they started incinerating, they came out with the fuel. So this fuel is now being utilized at a larger end. So people have, so it's just a spark which occurs, and then people enter into the process. And Walmart, we all know, they have entered into hybrid trucks. The hybrid trucks is being on the process, and they'll be entering into the mainstream somewhere in now it's a 2020 to 25, they have said. And other processes, we can say even in India, LG, Samsung, whenever we see they come out with advertisements such as now this LED is being replaced and with safe energy, like saving energy system, LED bulbs. And we can say the TCS, which have entered into agriculture utilization, agriculture waste utilization for their products. And we can see large amount of examples, live day-to-day examples in India also. But only thing in India, we need to go in for a mass productions. And we can also see that the production of biodiesel and biofuels are more in other countries rather than in India. So some of the other examples of green synthesis of organic carbonates from carbon dioxide, because this organic carbonates is really eating our carbon dioxide, which is being synthesized, chemical synthesis. The production and commercial epoxide building blocks. Here I'm not entering into this example because this is not my domain, it's civil engineering domain where they go for green buildings. And the green chemical processes using supercritical carbon dioxide is now this is hitting the industrial sector where they go for supercritical oxygen. High temperature and pressure, they're able to come out with the carbon dioxide. And the continuous hydrothermal flow synthesis and green process using biphasic catalysts. These are some of the examples which we can think about. And let me just give a light talk on biodiesels and biofuels. And because time consuming now it is, we'll just touch upon this biodiesels and biofuels. It's a hot topic, and we can see in southern state institutes, so many people are working on this biodiesel and biofuels. Each and every day we can see some paper journal publishing on this. So when we talk about biodiesel and biofuels, some new terminology has come into picture, that is a green diesel. Apart from this biodiesel and biofuels, what is green diesel about? It's a hydrocracking process, because hydrocracking process is high temperature efficient process, because it's dealing with very high elevated temperatures. But here our green diesel are able to crack it. It is able to break down the larger molecules which are found in vegetable oils and into shorter hydrocarbons that can be used in diesel engines. And we use this hydro-treated vegetable oil for this green diesel production. And it has literally the same properties as that of petroleum-based biodiesel. And gasoline can also be developed from this green diesel. And this is the latest technology going around this, invented somewhere in 2020s. Then you can think about this green diesel that is going to come into existence in near future. So coming into biofuel, you've got lot of substrates that can produce biofuel. But how to select these substrates? And in case people are working on biofuels, they know that we have different generations. The first generation, they were using any feedstock. Then they said, no, stop this feedstock that we are actually having it as food. Then the second generation came into existence where they produced non-food crops, that is the cellulosic biofuels. And then they said, okay, it is being harvested, we cannot have this, and it is depleting our energy sources. Then the third generation came into picture where we use algae. And now it is the fourth generation where this technology is utilizing the genetically optimized organisms. And then they capture the large amount of carbon which are genomically synthesized. And this genomically synthesized organisms capture the carbon dioxide from the atmosphere, because we know carbon dioxide is a major concern for us. And they capture this, that is carbon sequestration is done by the organisms. And then they capture and then they continue into the production of the biofuel. And we can see a major part over here, whatever it is, people start using it as a substrate for the biofuel production. And it can be anything ranging from coconut, molasses, palm, and you name it, and people are working on it. Either it be the husk or it can be the straw, it can be anything. So when we talk about the production process from bio sources, it is not only the biodiesel or biofuel. We have some other other products that is going to come out. We can see that biofuel, we started with the biofuel through biotechnological process. But what are the other major products that are going to come out is bioethanol, biobutanol, biohydrogen, biogas, and whatever you may is going to coming out as a product from the starch, cellulose, semicellulose, lignin. So why we are much concerned about this cellulose, semicellulose, or lignin? Because of the major concerns which actually give us the biofuel. If suppose we are going to talk about cellulose, it is highly stable polymer which consists of glucose. So that comes into the C6 category. And then the hemicellulose, they come into the C5 category. And then the lignin, they form both these categories where it forms the 10 to 25, around 10 to 25% of biomass by weight. So it has a long chain heterogeneous polymer and composed of largely phenyl groups. So we get large amount of products, and wherever we are able to tap, we'll be able to come out with newer products. And this shows how actually the processes can be defined on a treatment system. Suppose you're going to go in for fermentation, you can go for direct ethanol recovery from the sugar. And suppose I'm going to go for liquefaction process, then I enter into fermentation and come out with ethanol. So this lignocellulosic waste can have a different type of treatment systems. Either it can be chemical process, biochemical process, thermochemical process, and then we come out with different type of reactions. It can be combustion reaction, it can be gasification reaction, hydrocracking, or enzymatic route, or liquefaction, or pre-treatment methods, and pyrolysis, so that we have different stages of or different types of products. So if suppose you are going to go from lignocellulosic material to biochemical pathway, then we enter into bioethanol, biodiesel, biobutanol, methane, and then some specialty chemicals which are used in pharmaceutical industries. And suppose we are going to go for thermal cracking, then we can go for hydrogen and other products similar to methane, or gases through gasification, biogas example. So it depends only on the methodology in which we are going to adopt for our product base. So apart from plant sources, what are the other sources? The microorganisms which we are talking about. Algae. We live on algae because already it is a well-established route for biofuel system. What are the fungi which are responsible? We can see it's Trichoderma species and Aspergillus, which are much researched commercially, and more species are still under exploitation, namely Pichia or Candida or Saccharomyces, and all other species. They are able to come out with this biofuel or biodiesel. So we need to think or tap on these organisms, and these are all on the bacteria which can produce biobutanol. Zymomonas mobilis, right from the start, it is a cake for any microbiologist or enzymologist, where they tap the resource of the Zymomonas mobilis. It gives anything you ask for. And any microbiologist will also say Pseudomonas, but Pseudomonas are give everything but a lesser extent. But Zymomonas mobilis are a hot cake where people explore to any extent. They produce biobutanol, the largest, all BTEX compounds are able to produce. And coming to biohydrogen, biobutanol, bioethanol, biohydrogen, whatever we say, all these cyanobacteria can produce. And here in biohydrogen, we have two phases, that is lab fermentation and photofermentation. And the fermentation, depending upon the fermentation products, either you get lactic acid, butyric acid, butanol acetate, or you go for sulfur and non-sulfur compounds, either through their purple-based algae or your green-based algae or bacteria, whatever it is. And we are able to tap more amount of biohydrogen based on the organisms which we use. And we can genetically modify these organisms and produce and then extract it at that particular stage whenever and wherever it is required and called for. And these are some of the production processes of biohydrogen, where we can see the step-by-step process, and already this is into the process. And the production of biohydrogen have no greenhouse gas emission. That is a major advantage, and it is socio-economically advantage. And still people will say, why we are not producing? Only thing with the process, how to go about it in a continuous way. So that is the one we are lagging on, and we need to do a lot of research on this particular aspect. And traditionally speaking, the wet lab experiments are used to screen the organisms and the biohydrogen production, but the conventional approach is costly and time consuming, and this is the area where research is needed. And this says, slide says about how much of global production of biohydrogen using the agriculture products. So biohydrogen is not only into the through organisms, but also through the agricultural waste. And we need to explore a lot on this, because the ammonia that is being produced is being utilized by the plants for its survival. And here it is a complete recyclable process. The anaerobic digestion through biogas, as we all know, well-known in Tamil, the variety, well-known. But somehow we have come across a living that as age-old process. But now it is coming back again, where they need to think about gases through anaerobic digestion. Here, anaerobic digestion, anything coming out of animal waste can be used. It can be cattle manure, pig manure, chicken, whatever it is. In case it is going to be wastewater, the fats which are absolutely unused can be used for biogas production. And lots of works are being used with agriculture products such as sugar beet, food, and then the flotation and sludges which is being coming out of the industries are also used for biogas productions. And the microbial fuel cells, they have a distinctive future where these where these distinctive microbes are able to come out with electricity production. And some of the electrogens, we say, with respect to microbes that are producing electricity, can be geobacter species, can be Chevense species, or it can be Pseudomonas, or it can be Geothalliva, or it can be Geophyta. So we can use all this. Only thing here, we are using an anode and a cathode and the substrate as a glucose for the growth of the microbes, and it is able to produce microbial fuels, that is energy from microbes. So now from the microbes and the electricity, a new emerging technology has come, which is based on the microbial based diesel and microdiesel. That is the oleaginous microorganisms. What are these oleaginous microorganisms? These are defined as oleaginous species because they have the oil content in excess of 20% with respect to the biomass weight. Then you can tap this energy from them at that particular time. So what people do now, they paste this organism on the sheets where photocatalysis occurs. The organisms capture the carbon dioxide and they are directly giving us this energy. So we are able to produce conservative energy from these microorganisms. They accumulate more than 20% of the lipids on the cell dry weight, and these are based on these mainly based on these organisms. And these organisms can either synthesize either long chain fatty acids or short chain fatty acids, and this may be saturated fatty acids also. So it can be saturated, monosaturated, disaturated, and depending upon the ability of the microorganism, we can tap these organisms and directly apply on the sheets, keep it on the sunlight, and extract the energy from them. And this can be used as such. So this is one of the latest technology in which microorganisms are used for energy with the use of the sunlight. Here it is totally green, where no chemical are used. So this is 100% green technology. So if we think about the biofuel production, at large, we can see that nowhere India was there till 2017. And now India has started with biofuel production. And this, we should say that Reliance have started with this biofuel production. Once it enters into the energy department, with respect to bioenergy, we know we will surely succeed. Similar way how we are using our internal sources. So we have a bright future. Slowly will increase into the same way as we have seen our curve will rise, increasing right from the bottom to the top now, almost to the third stage. So we'll also enter into the biofuel production. So some of the industrial applications, it's a very meager, only few I have seen. Lots and lots of industrial applications are there into the system, and we can see that mostly it's oxidation, which is causing pollution that can be minimized, and methylation reactions where we can have methyl sulfide replaced by DMC. DMC, that is dimethyl carbonate, can have no deposits and they can easily be replaced as a green synthesis. And phosgene, which we have seen already, and the use of carbon dioxide reaction medium for asymmetric catalytic reactions are a better green production passage. So it is always important to teach the value of green concepts to the next generation. So they should learn to assess with this knowledge to adopt more susceptible and sustainable chemical practices throughout their academic and industrial career. And this is an interesting which when I was browsing just for our own presentation, NASA has entered into the green revolution. They have come out into lots of environmental protection programs. These are all the materials they have listed, which is of great concern for later construction of their own missiles. So what now they have found is, okay, all researchers come out with the alternative sources for all these. So we researchers can enter into any of these processes. Just enter into NASA and then you can see this list where they need an alternative solution from anywhere, any researcher from around the world. And they'll be able to take care of the process, and then you can go in for the direct production of the process. They have so much of listing, there's so much of opportunities for young researchers to look into these aspects. So all this I want to tell about. Of course, it is a brief knowledge. Only thing about the principles I want to say, but I lightly touched about all the green processes also. But this is a very, very vast work. Now I would like to say about my own group, which we have in Anna University. It is the bioproducts group. And we thrive here for the environmental protection and conservation. That is a crucial part for sustainable development. And this bioproducts group, the environmental motto has become the green chemistry, green products, and green world. And we only observe green route for the product development and aim to achieve environmental protection through the wide use of the natural resources. And all the products which we have quoted here are all pure chemical, non-chemical processes, but only the production process is taken from the chemical engineer's point of view. So the basic raw material will be a bio-based raw material, the end product will be bio-based, and the process will also be bio-based. And coming to conclusion, I would say here is, in today's environment, it's a matter of how long we live, because our earth is a critical portion due to man-made disasters. Go green engineering, and engineering should come into act to prevent or overcome environmental problems or to overcome environmental pollution. Always, we should never forget the 3 R's, that is reduce, recycle, and reuse. And for completing this session, I would say green engineering does not just improve the environment, it also improves the quality of our lives and supports economic stability. And green engineering benefits everyone. It's not for few people, it is for everyone around the globe. And it reduces pollution, saves energy, and improves the environment. Thank you for listening. Thank you all. Any queries can be answered.
That was a wonderful presentation, Radha.
Thank you.
Dr. Radha. And this is actually not only for the chemical engineers or people who are working on environment research, but it's for the entire society. The awareness is very much required. And Yuvraj is there. Hey, turn on your mic, Yuvraj. Yuvraj, turn on your mic.
1 second, I have little water. Let's talk to you.
Yes, yes. How are you, Yuvraj?
Can you hear me?
Yes, yes. Now I can hear. Hi, Prabhakar.
Thank you for your organizing this event. And really, I'm very proud. My classmate Radha has delivered an excellent presentation. But opening time plus start really informative.
You are all-time class representative, Yuvraj.
பண்ணிடலாம் ரெகுலரா தான் பண்ணிட்டு இருக்கீங்க பட் இருந்தாலும் நம்ம பேட்ச்மேட்ஸ் இத கம்யூனிகேட் பண்ண சிலர் வந்து ஜாயின் பண்ண முடியல யாரா வந்திருக்காங்க
No problem. It's already available in YouTube. Anytime they can.
Okay.
So Prabhakar is there. You know Prabhakar from instrumentation. Could you see?
Yeah.
Hi Radha. Hi Ushaa.
Hello, how are you? Nalla irken. How are you?
So amazed like how you had transformed from where you are. Never kana.
Oh my God.
So and the pure excitement I was just listening in. Monday la pochan vera vishayam, sorry, but you know very beautifully presented and wonderfully. Yes, yeah.
And Prabha is also here. She has a session tomorrow with us. Hi, Prabha.
Ushaa?
Hi.
Hi.
Could you see Prabhakar?
இல்லையே பிரபா தெரியலையே.
Yeah.
Not
Sure.
able to. Maybe in the let me change it.
You are in the
நீங்க
home, no? You will not be able to. You have to swipe the next.
oh
Yeah. Anybody, any of the participants can ask questions.
ஆதாரமே சொல்லணும். எப்படி வந்து ஃபர்ஸ்ட் இதுலயே பேட்டரி எல்லாம் எக்கோ எப்படி ஸ்பாயில் பண்ணுது என்ன அப்படின்ட்டு அதுக்கு வந்து ரீப்ளேஸ்மெண்ட்டுக்கு என்ன பண்ணலாம்? நான் பிசினஸ் ஆங்கிளா கேட்கிறேன். வாட் இஸ் த ரீப்ளேஸ்மெண்ட் ஃபார் திஸ்?
Electrical system vandachu. Bioelectrochemical system. Now you can replace the anode and cathode systems now. So that these electrolytes, I was explaining the last video, where we can have our organisms and glucose, so that this will lead to a better battery. Nano batteries, everything is entered into the research now. So we can list a lot on bioelectrics.
Hello. Yeah, good evening. This is Krishna Kumar calling from Qatar. How are you?
Good evening. Fine, how are you?
Fine, thanks. So it was a good presentation. Probably I joined little late because we have work up to 3:30, so there was. So maybe we can watch in the YouTube. No, Usha, it is available. Which channel?
Yeah.
Okay, please let us know. Okay, it's a good. Maybe we are in the other side of the spectrum of the fuel. Okay, I am in the LNG business, so you are doing something which is not okay. So I think I need to go through this in detail. I think it is still in the very nascent stage because of the R&D and other support probably required from the industry. I think this requires more kind of attention from the government as well as the others also, because of the cost involved in R&D, no? Because the commercial production is still the question mark, I believe. Correct, no, Radha?
I request other participants who are not talking to mute for some time until the other person completes their discussion, because giving lot of please. And whoever has the video can turn on your video. And Deepa, welcome to our webinar. Deepa, turn on your mic.
Hi, Radha. Yeah, Radha. Hi, Radha.
You're driving?
Yeah, I am driving. I'm not driving. So, as usual, rock. Radha rock. Okay, Nadula Radha of the speech அப்பப்ப கேட்டேன். But I was throughout in the presentation. Very nice presentation, Radha.
Thanks a lot.
Line roared.
Yes.
All the best. I didn't listen much to this, so அதனால எனக்கு very good presentation. You really rocked the presentation.
Yeah, just imagine how her students will be listening to our class.
Yeah. So நாளைக்கு யாரோடது உஷா?
Prabha.
My own students are here.
Okay. Yeah,
I think we should not do what we have been doing during the classes to our lecturers. Okay, now we ourselves have become lecturers. So
looking forward to just for Prabha's presentation tomorrow.
Yes.
Deepa and Grant. Okay.
No, it's really encouraging to see all the the classmates to come and join, irrespective of the timing, because the Prabhakar Arunmozhi is also there, but he is safely in the
overall Prabhakar பார்த்தேன். Usha, sorry to interrupt. Prabhakar பார்த்தேன். வேற யார் இருக்கா?
all others are hiding in YouTube.
யார் வேற யார் இருக்கா?
Arunmozhi is in YouTube.
Oh, Arunmozhi. Okay.
Actually, the Zoom room was full, Radha.
Radha, உனக்கு நிறைய attendance.
and then some from Sarbat gang also. Okay, maybe Yorajan and myself. Okay. I think you are.
யாரு triple E லேந்து join பண்ணலையா?
No, we don't know exactly who joined.
Oh, fine.
So any
Okay,
participants, any question?
Yeah.
Yes, please.
Any question? Anybody turn on your mic and you can ask your question. Praveen Kumar, Harishwar raised their hand.
Yes, ma'am. Hello, ma'am.
Yes, please go ahead.
Ma'am, I am Praveen Kumar. I'm student of Dr. Radha, professor. Thank you for inviting, ma'am, for a great lecture of green buildings, and I have to work together with ma'am, so I have to enjoyable. And ma'am, I have a question about the green technology, ma'am. I am already attending one of a lecture, ma'am, using a nuclear energy to be shrinkage into small energies. So, but the shrinkaging of small energies, it have a greater concentration. It will be same as wastages, ma'am.
Sure.
Like as reuse.
Whenever you're going to reduce the size, naturally you're going to increase the energy. Whether it is going to be mass or energy, when for the size reduction, naturally it will increase. So because we have so much of spaces where the reaction might occur. So this naturally increases the energy.
Yes, ma'am, but the energy also increased, but the waste concentration also increased by this, ma'am. So there is a problem to that, to land masses.
The energy that is being increased, naturally, whenever the molecules is becoming smaller, the reduction in size might not actually in it should be in the safer side than the macromolecules, I believe. I don't know how the nuclear energy which you are mentioning here, which of the nuclear energy, if you can tell me, so that you will be able to look into that. So whenever there is a size reduction, the mass reduction will not pollute that much as such. Of course, we have this nanoscale that is entering into the environment that also poses a problem. How to reduce this? Think about, and it depends on the type of the material used, type of.
Radha, what would you like to tell for this e-waste?
E-waste has to be completely avoided. Like now, technology has entered into the manufacturing process itself. So if I can tell you the example of this DuPont itself, they have made all the processes as zero waste. So once they have a waste, they take it to the next terminal so that it is being utilized. Rather than being wasted, now it is being utilized. They are making use of the products rather than letting into the system as a waste. So that is the point about zero discharge at all. Either it can be in a chemical or industry or automobile or e-waste management also. So the process itself is being changed. That's what I was telling about the material. Even before thinking about it, we need to think about the degradation process. Unless it is degraded, it's best to go for reusing the materials.
Anybody, any question? So that's all, I think. And thank you so much for your wonderful presentation. And the presentation, PPT slides were done very well. A lot of green.
Yes.
Yuvraj, you would like to ask her any question? மழிச்சு போட்டான்றோம்.
ஆமா, அதனால இப்போ என்ன ஒரு சந்தோஷம்னா பிரபா தீபா எல்லாம் பார்த்தது ஒரு சந்தோஷம். The thanks and the credit goes to you.
Very good, very good. I'm happy that you're all joined, first of all. Thank you, Prabhakar. Thank you so much.
Everybody.
ஒரு கிளாஸ்மேட் பார்க்கணும் அப்படின்ட்டு.
The credit goes to Ushaa. Because
I think we all met maybe 6 years back. Okay, after that we are seeing some faces together. At least, okay. Good, thanks.
No video is coming.
Sorry?
Hey, can you turn on your video? I can't see you.
My video is not working properly. That is why I couldn't turn on. Actually, in the laptop, there is some issue with my. Sorry, in my desktop there is some issue with my camera. Okay, so it is good that I can see at least some of you after a gap of 6 years. Okay, of course I met Radha sometime back. Other than that, I think maybe Yorajan, I met him during 2014. Probably I don't think whoever was there in the our meeting only we met. After that, very rare. So it's good that maybe we can have a Zoom meeting for our gathering also. Okay, apart from this kind of technical. Okay, maybe Yorajan. Okay, now since that social distancing, this is a new normal of Zoom. So okay, we can try that Zoom. What do you say?
Yeah, good idea.
Okay, we will post it in Unbenda. Let them check this. Okay, in our group.
And
Also.
I wish you all join even tomorrow.
Yes, sure.
Having a wonderful session with Prabha, Dr. Prabha.
Yes.
Yeah, this is the entire participants, Prabha. It's not only for our classmates, it's for all the participants who are watching this. So looking forward for your session. Sure. And thank you, Dr. Radha. And even yesterday we had a wonderful session with Dr. Bhuneshwari. We all feel proud of our classmates.
Yes.
Yep.
Yes.
Good.
Exactly. Good. So Prabhakar and others may be ready for an industrial panel discussion with me. Talk about the scenario of industry and the job prospects, how they should improve themselves for the students and all. It will be very, very a good eye-opener session we should have, definitely. You can throw some light on what's happening there. And they should come out of their books and classrooms. And that's what is my
that's true.
feel. They should just come out of the books and
Correct.
Okay, thank you.
Good. Yeah, looking forward for Prabha.
Yeah, please join. Come others also to join.
Friends who have joined and are patient listening. And thanks, Dr. once again.
Yeah, thank you, Radha.
Thank
you.
Thank you,
everyone.
all.
Thanks, Ushaa. Thanks, Prabhakar. Thanks, everyone.
Bye.
Bye. Bye, Prabhakar. Thanks.
Bye.
Thanks, Yuvraj.
Bye, Ushaa. Bye, Ushaa. Did you take the picture of our?
Radha. Yes, I have taken. Don't worry.
Yeah, post it in our group.
Yes.
Thank you. Bye-bye.
Okay. To the participants, I sent you the feedback link in the group, and the YouTube link already I have shared in the group. Thank you so much. And we'll all meet tomorrow. Thank you.
Yeah, tomorrow looking forward to people.
Take care.
Bye.
Yeah.
Thanks. Bye.